Hello class, this is spring force and Hooke's law. If you remember, Hooke was the person that Sir Isaac Newton burned the last living portrait of because he hated him so much, because they both did work on forces, and Newton wanted pretty much all the credit. Anyway, when we talk about spring force, we talk about using force of our spring is equal to the negative of some spring constant by the displacement of the spring. So I'm going to talk about each one of these, and this is what we call Hooke's law. Hooke found this. Not Newton, Hooke. So this is the actual force of the spring. But if you think about it, if you ever had a spring, you don't really feel any force on it unless you compress it first. That's what this part is. This is essentially how much, oops, that's an M, how much the spring has been squished. Or let's use a better word, has been compressed. And so we can say oftentimes, and you want to get used to this word, this is past equilibrium. Past the equilibrium point. So the equilibrium point is when your spring is just sitting there. It's at equilibrium. It doesn't feel stretched out. It doesn't feel compressed. Because this can also be compressed or stretched. If you pull on a string, it wants to go back to its other position. So this is compressed or stretched. So this is how much you change it past its equilibrium point. And last but not least, this is the spring constant. And this specifically is essentially how strong your spring is. So some springs are really weak, they have a low spring constant. Some springs are really strong, it's very hard to move them. Those have a high spring constant. So your units for this will be in Newton meters, which means how far you moved it has to be in meters. So this is going to be your initial position minus your final position. I'm sorry, final minus initial. I wrote it right, I said it wrong. Final minus the initial position, and it will be in meters. And then your newtons, or your force will of course be in newtons, because meters times newtons over meters times meters, cancel out your meters, you get newtons. Alright, so let's do a practice problem with this. Do try it on your own first. Alright, so your question is, if a 75 kilogram person is suspended by a spring, oh what fun, with a spring constant of K equals 5 newtons per meter, how far has the spring been stretched past its equilibrium point? So do try this on your own first. You have the spring law in front of you, or Hooke's law. Try to figure out how far it's been stretched past its equilibrium point. As always, draw a free body diagram first. So here we are with our free body diagram. We have a person. He's being suspended by the string, but he does still have gravity. This person is now also being held up by the spring, so they're suspended, so they're not moving. Hey, hopefully that tells you something. So FG, we know how much mass he has. So this is equal to 75 kilograms. So it's the mass times g, or the acceleration on Earth, which is 9.8, or 10, because I am rounding, meters per second squared. You'll get 750 newtons going down, so we could call that negative. Therefore, since he's not moving, how much force does a spring has? Hopefully you remember, it's got to be equal and opposite because he's not moving. Which really all I'm saying is sigma. Remember, sigma means sum. You add them up. Sigma in the y direction of this would be 750 minus 750. Therefore, overall, it's equal to 0. No net force. So now we know what our spring constant is equal to, but we want to know how far has it been stretched past its equilibrium point. Or essentially, we want to know, hey, what was the change in x? So to do this, set up your problem. We know the spring constant, it's right here. So now we just need to plug into the force of our spring is equal to the negative of the spring constant times the delta x. We know most of these things because we know the force must be 750 newtons. We know the spring constant is 5,000 newtons per meter. And we are trying to solve for delta x. So hopefully you can look at this and be like, hey, I think I know what I need to do here. We're solving for x, so we of course want to get rid of this. It's next to our x, get it away. Divide by your Newton meters, these cancel out. Do it to both sides. Your newtons cancel out, and you are left just with meters. Plug this into your calculator, and you get 750 divided by 5,000, gives you 0.15 meters is equal to your delta x. Yay, congratulations, Merry Christmas. So, does this make sense? Yeah, 5,000 newtons per meter is a huge spring constant. That's an incredibly strong spring. So it's going by only a little over a tenth and a little less than a fifth of a meter. So, yes, this is a huge, huge spring constant. So your springs, even though it's carrying a grown person, is not going to be extended too much. Alright, hopefully this gives you some idea of how to do your springs, and I will see you on Thursday.